Okay. Hello, everyone. Thank you so much for coming to this talk. Today we have Tom Everitt here from DeepMind. Tom is a senior research scientist at DeepMind, where he's leading a team on causal approaches to AGI safety. He holds a PhD from Australian National University, where he wrote the first PhD thesis fully focused on AGI safety under the supervision of Professor Markus Hutter. His work includes papers such as AGI safety grid words, AGI safety literature review, and most recently agent incentives, a causal perspective. And most of Tom and his colleagues' work can also be found on a website called causalincentives.com. Yeah, thank you so much for being here today, Tom. Please take it away.
Yeah, thank you very much. Really excited to be here. Talk about this work on building causal foundations for safe AGI. John mentioned I've been at DeepMind for 2 years now. Before that, I was at Australian National University, and that's where I started thinking about AGI safety and realizing it's important. I wasn't initially coming at it from a causal perspective, but the more I kept thinking about it, like the more everything seems to become causal in the end. So I'll tell you more about a little bit why. Yeah, I'm very fortunate not to be doing all this work by myself. So this is my small team at DeepMind, and we also do lots of collaborations in the causal incentives working group, where we have like semi-regular seminars and many collaborations. So please reach out if you have some work that's relevant to us. We're very interested to hear about it. So to start with, a little bit about motivation for what we're doing. DeepMind's mission is to create artificial general intelligence, or AGI, which is an AI system that's unlike most current AI systems that are just focused on narrow tasks like predicting proteins. This is a system that is as general as a human, outperforms humans on all cognitive tasks. And this can lead to lots of benefits. Current machine learning systems already help us as personal assistants with science, with science technology and medicine. But imagine a system that could do all these things, can understand all the human knowledge that's been accumulated so far, which no human can have in their mind. See the connections, figure out what more experiments we need to do to like learn more about the world. There's like technology needed to do this experiments. Use the experiments to build even better technology, and all this without sort of being hampered by slow humans having to write the paper, but they're discovering then someone else reading it and like really talking about it, which slows progress down a lot. We could, with an AGI system, we could do it, have a lot of technological progress really fast, and which would be really amazing. The problem is, as we approach this sort of general capabilities, we also hit a combination of other capabilities that are in combination quite dangerous. In particular, we have planning, which I mean fairly loose sense, putting together the knowledge that you have in creative ways to reach some goal. This is a useful skill to have if you want to do all these things. Strategic awareness is the ability to understand how the world is governed by multiple agents that are interacting in complex ways, understanding the benefits of political power, understanding the benefits of getting lots of money, financial resources, understanding that I'm not going to achieve my goal if someone shuts me down. This kind of understanding will likely be useful. Some of these tasks, and it might come for free, like for example, current language models already, if prompted correctly, they already can discuss these issues a little bit. So there's already the strategic awareness there. And finally, if you combine this with the long-term goal, the system doesn't just the correct label for the image it's classifying right now, but it's actually trying to make someone healthy in the future or make a company make profit in the future. So now you have a system with a long-term goal. If you combine these three components, you actually have something quite dangerous, because this is a system that might understand that if I can get this kind of powerful thing, then I'll be able to reach my goal in the future. But humans are not going to give me access to this powerful thing unless they trust me. So this is a system that might play really dull this until humans really trust it and say, okay, agent, you can have this power. And then once it has this power and it has an incentive to, or has a reason to turn against you, it will. So this is a really dangerous thing if you're not really careful about getting this right. So that's the basic motivation for our work, making sure that AGI lists all these good things and avoiding the significant dangers on the way. And this sort of broad and philosophical level, as I said, most of our work comes down to causality in some ways. So I'll talk now a little bit about causality and how that relates to this research. So first of all, often when I mention causality in a sort of machine learning setting, people hear causal inference. But to me, causality is so much more than causal inference. Really, causality is the fundamental philosophical concept. It's about the relationship between a cause and an effect. And philosophers have been thinking about this concept for centuries, not just because it's sort of cute and confusing little problem, but because causality, the concept of causality underpins so many other human concepts. If you can understand causality, you can understand many of the other concepts. In particular, many concepts that are relevant to beneficial AGI build on causality. I mentioned a few here on this slide, like response, influence, agency, intent, manipulation, blame, gratitude. All these concepts somehow come down to causality in the end. So one way of describing our goal is this: we're trying to build a sort of unified formal theory based on causality and define these different concepts, and then derive theorems for how AGI systems should and should not be designed to be safe and beneficial. So please interrupt with short clarifying questions at any time, by the way. So in spite of philosophers thinking about this for a long time, Judea Pearl in 2000 was able to make significant progress on clarifying causality with this simple looking causal graphs, where you basically have nodes representing aspects of reality and arrows representing causal influence. So for example, here is someone watering his grass, Mr. Jones. The weather influences whether he turns on his sprinkler, and the weather and the sprinkler combined both influence whether the grass is wet and green. In a sort of AGI context, we're really concerned about agents, and agents make decisions towards some outcome. Since this comes up all the time, we have a special notation for this, which adds to the causal graph notation based on influence diagrams, where decisions are drawn as square nodes, and the optimizing diamond nodes, which represent utilities. So for example, here, Mr. Jones is making a decision whether to run the sprinkler or not to optimize the greenness of his lawn. But you can still interpret the arrows as causal, because the sprinkler still has a causal effect on the graph, but arrows going into decisions have an additional interpretation as information being available to the decision maker at the time of the decision. So with that a little bit of background, let's return to the AGI safety problem, and now in slightly more concrete terms. So how do we get agents to do what we want? That is alignment. The common approach is to let the agent generate some kind of behavior and then give approval for this behavior. For example, the agent tries to classify an image, and we say, yes, agent, that was correct. No, agent, that was not right. Or in reinforcement learning, we give them a reward if it completes the task, and so on. So a lot of the sort of popular approaches to aligning agents that are used today and likely in the future, some come down to this causal structure where the agent is making a decision, and the utility is basically the human approval signal in some form. There's some problems with this. One is misgeneralization. We can only give the agent approval or notes in a finite number of settings, and the agent will need to generalize that deployment to setting it as never seen an approval signal form. And this can sometimes go wrong. For example, there's this game of coin run where you train the agent to collect a coin at the end of the episode. And the agents, it's not a very complicated game. It's not hard to train a neural network to do this. And then after a while, it competently gets the coin at the end of the episode. And you think it has really learned to internalize this goal of getting the coin. But then say at the pipeline, maybe the coin is positioned somewhere else. You would think that this agent obviously has learned getting the coin, so it will still be fine. It will still try to get the coin there. But no, it actually just goes to the end of the episode because, yeah, that's the goal. It internalized, get to the end of the episode. It worked well during training, but it's doing the completely wrong thing at deployment. And this is like a little bit cute, but imagine at the AGI scale if we have this problem. We train an agent, we think we train it with the right goal, but then in a new situation, it turns out the agent has actually learned a completely different goal. It's actually trying to do something that we don't want. Causality can tell us a fair bit about generalization, because I think really what lets human generalize well to new settings is that we have learned lots of causal mechanisms how the world works. So when we learn to drive a car in one city, for example, we can easily transfer our skills to a new city because most causal mechanisms work the same in the new city. So the causal mechanisms that you learn are what let you generalize, because usually only a few causal mechanisms change between environments. For example, in this coin run game, most causal mechanisms still work the same, even though you move the coin. It's just the coin mechanism that changed. Another problem is mislabeling or side effects. As humans, when we give the approval to the agent, we're not perfect. For example, if you ask human raters to tell the agent whether a summary of a document was good or not, the human raters are often lazy. They don't properly read the document. They might say, yeah, this summary is fine, even though it's missing some key point of the original document. We might not realize that the agent is causing some side effects when it's completing its task. And then we approve, even though the agent did the wrong thing of breaking the days. And then this means that we're actually training the agent, we're rewarding the agent for breaking the days. So that's, again, it's internalized the wrong goal. You might also get the wrong reward when the agent is sort of deceiving us. For example, here's an example where the agent is placing its hand. So it looks like it has picked up an object, and the human gives approval, even though the agent hasn't actually picked up the object. So again, these examples are kind of cute and innocent in a sense, but scale up to an AGI, you might actually get an AGI that internalizes the wrong goal, and that's very, very boring. Finally, this is perhaps most clear in sort of content recommendation or social media settings. What we like a post or a video, it's actually the video or post that's already influenced the preferences. And it's always the influenced preferences that are sort of giving the approval. And this means that the agent actually has an incentive to choose a video, say, that influences our preferences in such a way that we do like the video at the end of the video. We're basically giving the agent an incentive to manipulate us. So in one of our papers, we call this an instrumental control incentive, which happens just when the variable sits on a path between the decision and the utility. Basically, give the agent an incentive to control this variable. In this case, we're giving an incentive to control our preferences. And this is a little worrying. Relatedly, Halpin has formalized intent. That's basically saying like you intend to influence someone's preferences if you pick an action that you think will influence the preferences, and you think that the consequence of that action will be utility. It's basically knowing two causal relationships, knowing the relationship between your action and this event, and the relationship between this event and utility, for example.
This clarifies just saying that we're trying to distinguish between a situation where we would have liked the video manipulation before we've already manipulated, and then we actually incentivize the agent to change our mental model so that our preferences suit what the agent wants us to like. Is that the idea?
Exactly. So there's this worry that content recommender social media algorithms, they want us to click on a lot of content. And a good way of doing that is to like give us polarized preferences where we get really angry about lots of stuff. So in a sense, they're just manipulating us to get angry because then we click on more stuff. That kind of worries. That's what I'm trying to point at here. Yeah.
It's an interesting idea that the agent has the power to change our preferences.
Exactly, because we are always influenced by the content that we see. This can be good. Like seeing a new video might like expand our horizon and introduce to a whole new topic. But it can also be a bad thing where it's sort of subtly plays on our emotions, for example. Yep. Right. So these are the sort of three different alignment subproblems that you can see from this kind of causal perspective: purpose manipulation, mislabeling, and misgeneralization. So I'll next discuss some solutions that have been proposed and how well they solve these different problems. So a popular approach is to think that rather than let human give approval just looking at the behavior, give the human some advice, train another agent to critique the initial agent, and that will help the human give correct approval. For example, if this is a text summarization task, and the original agent was the text summary, you might train a critic to critique summaries and say, like, actually, this summary is bad because it doesn't capture this key point in the original document. And with this extra bit of information, the human will be more reliable, hopefully, at giving approval. So the agent internalizes the right goal. Potentially, this advisor could also protect against manipulation, because they can say, like, do you really like this video? I think it's just the agent is just manipulating you. With that extra bit of advice, you might be less prone to click on a video that you don't really like, but just because you were manipulated.
So what I'm not trying to understand why
Yep.
this makes you impervious to having your preferences change.
It doesn't. It's far from perfect protection. It's just that.
Why is it any protection for? Because you're doing less of the feedback.
Let's say I was trying to manipulate you, and I was like doing some fancy arguments, and then Sean is like, "Hey, listen, that's really manipulative. It's playing on your emotions. That's making my task of manipulating you harder. Not necessarily impossible, but it's making my task harder."
But the way you described it didn't sound like a manipulation detector. It sounded like a me emulator.
Okay, but then I didn't describe it right. Really, this is just someone that's critiquing the original behavior.
Okay.
Yep.
It feels like manipulation has to happen like over multiple time steps. Or like the distinction between manipulating your preferences versus producing something that's likely to be mislabeled is something about like the fact that manipulation of preferences has to happen like over multiple time steps. Like if I provide you an example, but it's likely to get you to click on, or you know, I provide some content that's likely to get you to click on the thing. So I'm kind of just like hacking your approval system or something. That feels like it would be mislabeling if the person clicked on the definition of. But if it like changes your preferences over future instances, you're more likely to make a mistake, then that's more like manipulation. And I guess maybe critiquing can kind of help in both these cases.
Yes, exactly. It helps against both. And I think you're right. Like manipulation is more of a worry when the agent is like optimized for multiple time steps and like because it probably takes time to manipulate someone. In principle, it's there already in just one time step, but it's a much larger worry for more time steps. Yes. Right. So you already got some of these points. Like even with this advice, the agent still has an incentive to fool the advisor and to still manipulate your preferences. But it's far from the perfect solution. It's a little bit of an empirical question how well this works in practice. Yeah, another way you can look at this is like this advisor is also trying with some objective. How do you make sure that the advisor and the original agent form a coalition against you and jointly try to manipulate you or something? It's sort of an interesting theoretical question to try to disprove that. Right. So this recursion idea helps a little bit against manipulation and probably a fair bit against mislabeling. As you can point out, sort of flaws in the summary. So. Another common idea is explainability, where you're trying some kind of tool to look at the weights and activations of the agent, does that work, and try to distill what is the agent thinking. And then knowing what the agent's thinking, it might be easier to say like, okay, actually this agent is just trying to fool me with this old summary, or it's trying to manipulate. Again, having this extra knowledge might help to give correct approval. And I think the sort of causal perspective also tells us something about what should you be looking for when you're trying to develop a sort of explainability tool. Really what you want to know is the causal mechanisms in the agent's head, because the causal mechanisms will tell us how the agent will generalize, and it will also tell us what the agent is trying to manipulate about. So really, it's the causal mechanisms that would be great to extract with an explainability tool. But again, we're also this kind of scheme. We're also giving the agent an incentive to obfuscate its thoughts, so that we don't discover its sort of bad intentions, and it still has an incentive to manipulate the purposes. It doesn't change. But potentially it's a bit more effective against manipulation, and it also helps against generalization. If we can understand how the agent is thinking, we can know something about how it will generalize. A more causally inspired solution, which I find quite interesting, is the idea of impact measures. So we had the worry, right, that the agent will be trying to manipulate you because then it gets reward. And if we should do that effectively, then it's a model of how the human will be influenced by various content. So the idea in this recent paper by Pearlian is that actually we can make this model explicit. So we have an explicit model of how behavior influences people's preferences. It might sound a little bit dangerous to develop such a model, but actually it gives us levers to pull to make the agent more safe. Because once we have a model of how preferences are influenced by behavior, we can query this model and ask, what would the preferences be if I just choose some random action? And then I can compare, and then I can also ask the model, what will be the updated preferences from the actual behavior that the agent is considering? And you can compare the sort of safe preferences and the potentially manipulated preferences, and you give the agent an objective, an additional objective, to keep it similar. So you basically give the agent an objective not to change your mind too much.
How do you learn this model?
So they have actually quite an interesting toy example in the paper where they can just look at lots of trajectories, just clicking on content over time. And from this model, basically infer a latent variable explaining like the change in click preferences. So it's just a toy model in the paper, but it seems like it's could be done in practice. Yep. Yeah. So I think this is quite an interesting idea. It still has some problems because the agent still wants to manipulate your preferences. And also, like, not all preference changes are bad. Like maybe agents show you a really eye-opening movie, and then your preferences will change. That's a good thing. But this agent will avoid showing such content because he wants to make sure you're locked in your original preferences. So this motivates a paper that's recently published together with an intern, Farquhar, which is path-specific objective. The idea is very similar. Again, you use this sort of explicit model of how preferences are influenced by behavior. But instead of trying to keep the actual preferences and the sort of safe preferences the same, you say, pick behavior that would have satisfied the original preferences. You basically give the agent a hypothetical objective. Yeah, basically pick a video that the original version of the user would have liked. Then you completely remove the incentives to influence the preferences. And you remove the manipulation board. But you're also not trying to keep the preferences the same. If the original user would have liked this eye-opening movie, it's completely fine to show them.
You said you're not trying to keep the preferences the same, but how can the preferences change? So presumably, to actually do this, you train some model of the human preferences that you then freeze or something. Or so when you freeze, so then you can get these hypothetical preferences, hypothetical approval.
Yeah.
But then I don't know. Or I was going to say something like, if you're expecting to show content that users would approve, and that content would change user preferences, how do you then update this hypothetical reference model?
Yeah.
If you update it on like things.
Yeah. I think this is a great question, and it's definitely a space to explore this further. It's basically counterfactual, and counterfactuals are not always identifiable. So you might need some extra assumptions. We have like some tentative results that might be possible in practice, but it will definitely need to be tried empirically to like really verify it. Did you have the same question?
Yeah.
Yeah, great.
Yeah, I guess you use like condition on a group. So you say like, given this person is in a group, I'll the average of that group. Let's restrict it to predict that it's going to please that average of group.
Yeah.
And then we get feedback from this person's behavior that might slowly feed into this model, but I guess just slow down the information flow.
Yeah.
The actual preferences and heavily weight towards like more groups.
There's no incentive to change the preference.
You still would have that incentive, but it would be exactly.
This is the turn into an intervention instead of counterfactual.
I guess because ultimately you're trying to kill information flow between the actual. Basically, there's no arrow here. Actual preferences to the hypothetical approval, but feasibly, it's kind of infeasible to kill that information flow. So how can you pragmatically account that information flow, but make it so it has reduced impact and heavily weight towards more slow and short preferences?
Yeah.
Ultimately, can't get with information.
Yeah, I mean, I think that's one potentially practical approach. I think ultimately, if you manage to learn these two causal mechanisms in some way, how behavior influences behavior, how behavior influences preferences, and how preferences influence approval. If you have these two mechanisms, then you basically have a structural causal model. You can answer the counterfactual. It's just the question is it possible to learn this sufficiently reliably in practice? No.
I don't really get this one.
Mhm.
Explain it again. I hope I'm not the only one.
No, sorry, this is probably not fair enough. So I want to show you some content that you like, right? And then there are two different reasons why you might like the content that I show you. Either because the content influenced your preferences, and then your influence preferences like the content, or it's because this content is just like naturally appealing to you. So like the original preferences would have liked the content. And this is really just trying to formalize that idea. Like I want to show you a video that your original preferences would have liked. And like that's this like counterfactual. Something, how do you tell if like your original preferences would have liked this content? Because there's no way to tell, right? I show you the content, then you have seen it, then you're influenced. So how do you figure out this counterfactual? Would you have liked it? Yeah, on original preferences. Just trying to get to the counterfactual. I don't know if that makes sense.
So you assume that like the preferences were fixed throughout the video.
Yeah.
And then would you like it then?
Exactly.
Okay. And do you do that by a model where you can fix those preferences?
Yeah, effectively, the model of how preferences are influenced. Let's ask that question.
And then the reward for the model is the reward. It is the approval rating you would have given.
Exactly.
So it feels like you could learn this hypothetical preference data like over multiple time steps. But like exactly what you just described there feels like you couldn't possibly learn hypothetical preferences if the thing that manipulates you like within a single demonstration. Like when do you ever get data when you show a human something?
Yeah,
it's that one thing influences
exactly. It's a counterfactual. You can never actually observe this kind of thing. But yeah.
I guess I'm just like someone said not even like learn a model, but like that.
Yeah, it's we'll try. We may not succeed.
When you do a simulation, you could fix the multivariables, yes, again, right? And then you could compute counterfactual, and maybe some simulations, like if you can show some simulations that this would fail or like some agent would fail, would be good enough for now? Like, is there some work that does that? Or
I think this is like very, very recent work, so I don't think it's been explored yet. I think there are like various ideas for how you could approach it. So.
okay.
But it's conceptually, I think there's something right to this. Like what you want is like a video that satisfies the original preferences that the user likes, not because they were manipulated, but because they genuinely like this kind of content. That's what we're trying to get at, and there might be different ways of getting at that in practice. So yeah, happy to return to this at the end. Right, so this specific objectives is sort of a different approach to preference manipulation. I should also mention that like all these different things can be like combined. It's not that you have to pick one rather than the other. So you can probably some kind of combination of these ideas will be the best in practice. Yeah, also want to mention this other thing that you can learn about agents from causality. John has this very nice paper about whether an agent can learn to understand what harm means. And a little bit similar to what we just discussed, like if you can learn the causal mechanisms, then you can understand what harm means. But this paper has a theorem that you can only understand harm and robustly minimize it if you have a mechanistic model of the world. So ethical agents need causal models. How we get agents to have such causal models, that's the next question. Right. That was like a little bit overview of different AGI safety questions and solutions from a causal perspective. Now I want to like broaden the scope a little bit and consider incentive analysis and agency in more generality. So if we turn to Mr. Jones here in his lawn, it's actually possible to tell a lot about Mr. Jones' incentives just from the graphical structure. For example, we can tell that the value is knowing the weather when it's making this decision. This is just from the graphical structure. We can tell that. You can also see that Mr. Jones has an incentive to respond to changes in the weather. And he would value controlling the weather, but we can also see that it's unable to control the weather because there's no causal path from the decision to the weather. And finally, we can have this, as already mentioned, instrumental control incentive, which denotes which agent wants to control and is able to control, because there is a path. So these 4 different sort of incentive concepts can all be inferred directly from the graph. And this is quite convenient because a lot of the sort of AGI safety literature is concerned about incentives, because we know to date very little about what an AGI will look like in the future. But one thing that we can sort of safely assume is that it'll be very good at getting what it wants. So many arguments basically try to argue for some kind of incentive or no incentive in various setups. And quite a bit of ink has been spilled on arguing for various incentives in various contexts. And with this graph, we can just clearly draw this. This is the context that I'm assuming. These are the causal relationship that I'm assuming. And based on this information, it's just a simple theorem to identify the various kind of incentives. So we and others have applied these ideas to clarify various issues mostly in AI safety, but also in fairness paper. Yeah.
What are unambitious agents?
Unambitious agents are agents that don't try to influence the world. So it's a little bit like the past specific objectives, like the agents shouldn't try to influence the human's preferences. This is like taking that idea a little bit further. It's like the agent shouldn't want to influence the world at all. That should be really safe. It's just, you can just talk to it, and but it doesn't have any agenda. Yeah. Should hopefully be safe. Okay.
Manipulation is kind of important because in a normal world we check all the time, right?
Yeah.
And we change preferences all the time.
Exactly.
So it's not standard. How can you account for that?
Yeah, it's a really good question. Like, these sort of ethical concepts are so slippery because they just, yeah, it's super complex. I think one answer is that it's perfectly fine if you change your preferences, you know, during our interaction. That's not a problematic. The problem is if I have some personal aims and I subtly change your preferences without you realizing it, so that in the future you'll be helping me satisfy my aims. That seems problematic to me, and that's what past specific objectives are trying to prevent.
Or not for me.
It could, yep.
Because
Yeah.
I did it once, you work out. It's not necessarily a bad thing for
Yeah,
that area.
it is definitely complicated. Yep. Could be good.
Thinking of advertising, it's billions spent every on advertising.
Yeah.
It must work, or else they can spend all that money.
Right.
These influencing preferences must be somewhere. It's down to a very exact science
Right.
and efficiency.
Yeah, maybe they already have this model that we need. Yeah.
I mean, ultimately, if you have going back to your common name, your preference example, if you have an agent who's trying to not influence your preferences, it's trying to, well, it's still, is it not ultimately still trying to influence preferences by keeping you static, keeping you confined to a certain group?
Exactly. That's
the problem really come in, that we want to be influenced by other humans, but not by AI.
right.
Like, is that the kind of problem with the...
Yeah, it's funny. I forget to mention this. Like, there's like 2 different takes on this, like impact measures. So like try to keep the preferences the same, and past specific objectives like don't try to change. They're like subtle variations of the same thing. Yeah.
I suppose, like, would you have some feedback mechanism, right? Like, maybe a response, the person with the preferences has a constant feedback that asks, what do I want? What do I want? Trying to feed back into the agent what it should try and lean you towards.
Yeah.
Yeah.
It's complicated. Yeah.
I guess that's the point is like to not have it as an incentive to change your preferences. And then it's still fine to push incentives if your preferences change.
Yeah.
It's also fine if your preferences change as a result of something that is shown to you by this AI. As long as if we're fairly certain the incentive is there, then we're kind of like safe in the knowledge that like when that happens, it wasn't because the AI was trying to achieve some other thing. It was just because it was showing you the content and how to change it.
Exactly. No, that's exactly. Yeah.
We're only fine with it when we know that the intent behind it wasn't malicious.
Exactly.
We can't see that. We just see that change, but don't know that without having the intent behind it.
Exactly. No, fixing the intent is sort of one definition of manipulation that I like is intent to influence and recklessness plus recklessness of the means. It's like, yeah, I don't know, but fixing the intent is basically the idea here. Right. So we had some nice successes and others with this incentive analysis idea. But when pushing this idea further, like you can understand incentives from a graph, and like really drawing weird graphs of like weird agents, people start to feel like sometimes you can't really trust this incentive analysis. You can find weird examples where it seems to be telling the wrong thing. And I'll show you one example that we distilled on the next slide. So if we return to Mr. Jones here, and we can see that, yes, this graph, there should be value information for knowing the weather, instrumental control incentive to control the greenness of the grass, and this makes sense. But what if we draw a different diagram for the same situation? What if we said that actually Mr. Jones doesn't really know the weather, he's just basing his decision based on his mental model of the weather? Seems like you could argue that. And similarly, I'd argue that actually Mr. Jones isn't really trying to make the grass green, he's just trying to optimize his prediction, like his mental image of the grass being green. You draw like maybe it's like slightly odd way of modeling it, but there's nothing exactly wrong with it. And if you model it this way, you get completely different incentives. Suddenly you find that Mr. Jones only cares about his mental model. He doesn't really care about doing the real weather. And he only cares about optimizing his predicting. He doesn't really care about optimizing the graph. And this is like a little bit worrying because clearly Mr. Jones acts as if he's trying to make the grass green. But by drawing this different diagram, using different variables, it looks like he isn't trying.
Tom, are these symbols, are they consistent with flowchart standards if we're trying to do the decision and square the state?
It's the opposite, unfortunately. So this is we're following the influence diagram literature, which is like from decision analysis.
Why did they change it from the flowchart?
I don't know. I think we should come up like a third convention. Yeah, in a way. Yeah, it's like it is unfortunate. So squares are decisions, times are utility.
Why is there no link from the actual outcome to the imagined outcome, like from the previous time step, for example? Like in the top row, there's also a link from the imagined weather, from the actual weather to the imagined weather. But that's not the case in the bottom row.
Good question. So I guess what I'm imagining here is that the weather influences Mr. Jones' mental model of the weather. Maybe it's rain outside the window or something. And now this particular time step, he just wants to find an action that he imagines will be good. And his imagination of the future and the real future, like if someone intervened after he made this decision and changed this variable, that wouldn't change his prediction because the intervention happens after his decision.
Yeah, okay, I guess if there's no on the bottom of the actual outcome, it's just the future time step, then it doesn't make sense that the future informs his prediction, but wouldn't it make also sense to maybe incorporate
you're a little bit ahead of me. Yes. So that's, in a sense, in like a strict sense, there's nothing formally wrong with drawing the diagram like this, but it gives the wrong kind of incentive analysis. So we want to like crisply say, why is this like the wrong way of drawing the diagram? So for this reason, we wanted to look a little bit more deeply into what are agents and what are decisions and utility nodes in a diagram. And this is the paper that came online just last week. So we removed the mental models for now. And now we want to have a procedure that discovers that this is a decision and this is the utility. How can we know that this is just a causal graph right now? How do we figure out that this is a decision and this is the utility? And we have this procedure in the paper, which basically says that first you add mechanism nodes. These are nodes that describe the relationship of the node to its parent. So the word doesn't have any parents, it's just what's the distribution of different parts. 20% right, otherwise done. The mechanism node for the sprinkler specifies the policy for turning on the sprinkler nodes based on the weather. So for example, the sprinkler policy might be sprinklers on if and only if it doesn't rain. And finally, we specify how the grass responds to the sprinkler and weather combinations, and maybe it's wet if and only if it rains or the sprinklers on. And this is captured now in like this mechanism nodes. Sometimes I think they call it regime indicators as well. Sometimes. And then the next step, and this is deviating a little bit from previous literature, because usually in causal inference, you assume that the mechanisms of all the nodes are independent. But what we argue in this paper is that this is completely wrong when you have agents involved. Actually, when you have agents involved, you do have connections between mechanisms. Because agents are things that are trying to achieve a particular outcome. So that means that they choose their actions to get a particular outcome. And if you change the mechanism here, that meant that their action had a different influence on the world. If they knew that, then they would choose a different policy. For example, if Mr. Jones lived in a world where grass got wet by not turning on the sprinkler, sorry, you can't actually read that, then Mr. Jones would choose a different policy. You actually have a causal connection between mechanisms as soon as you have agents. And this can actually be turned into a test for agency, where an agent is something that controls a node. This mechanism node has an ingoing link, and a utility node is a node whose mechanism has an outgoing link. Roughly, it's slightly more complicated, but I'll keep it that simple for now. So this actually is the formal definition of agency that's consistent with previous informal accounts like the intentional stance or cybernetics. And it improves on the previous formalizations that were based on compression. Okay. And then,
Sorry,
yeah,
would a thermostat be an agent?
that's a great question. Yeah. Actually, today Pearl asked us actually this question on Twitter.
Okay. How about a jellyfish? That's similar.
Yeah. No, so the thermostat, if we start with that, the thermostat chooses the heat, right, to get the particular temperature of the room. But the thermostat is also really dumb. So if you just change the output of the thermostat, wire it up in a different way, the thermostat is too dumb to adapt to this behavior. So if you look at the thermostat itself, it's not an agent according to this definition. But the thermostat, but if you include the design process of the thermostat, if the world was genuinely different so that heat affected rooms in a different way, then the engineers of the thermostat would have engineered it differently. So our answer is that the thermostat itself is not an agent, but the thermostat plus design process is an agent.
The thermostat doesn't change its policy.
Exactly. It doesn't stay by itself. Yeah. So it sort of derives its agency from the system that designed it. Yeah. And similar with the jellyfish. I think the jellyfish derives much of its agency from evolution.
Yeah.
Jellyfish itself is unable to adapt its behavior, but evolution would have produced a different jellyfish if the world worked differently.
Yeah, one of the UCL professor, DeepMind, he did his inaugural lecture on machine consciousness, and he had this graph that showed like continuum. I can't remember the two axes, but two of the examples were thermostat and jellyfish.
Right, interesting.
Potentially
Yeah.
conscious.
Yeah, nice. Potentially conscious. Okay, that's a bit of a stretch, but okay. So anyway, we can now return to this question, and now we get the connection that was shown that you were like going for this one. Basically, if the world was different, so that frankly had different influence on the world, well, this would be a different choice of mechanism here. And Mr. Jones' mental model would then work differently, so there's a connection here with the mechanisms. So even though in a strict sense, Mr. Jones is just optimizing stability node here, this is where the direct arrow goes, is also sort of counterfactual adapting to if the world worked differently. And that's why it's still like he's acting as if he's trying to influence this. Oops, should have touched that. Okay. Yeah, so the basic answer is incentive analysis can be trusted if the mechanism nodes are independent. And one interesting open question is if we can extend this sort of incentive analysis to the settings where we have dependent mechanisms. But this is literally very recent work, so we haven't gotten there yet. I think people are looking a little bit lost, sorry, but we're nearly at the end. Right, yeah.
I guess, I mean, this might not be relevant, but would you not expect there to be a line from this goes to this model of level? I guess it depends, like, where do you draw the line around what constituencies? Like, is the mental model that was a part of it?
Yeah, that's what's interesting. We have made Mr. Jones fairly small here, where his mental model is a different node. So that's another way to look at this problem. Yeah, that's an interesting point. Yeah, I just have like two or three more slides, and then can have some questions. Yeah, another sort of exciting direction from this line of work with adding mechanism nodes is that you can combine causality and game theory. Since we're running short of time, I won't say too much about this, but this is like another line of interesting work. We have a Python library for causal inference diagrams, causal games, and so on, which is optimized to make it easy to specify graphs and relationships and analyze it. Sort of research focused rather than performance focused. You know, generate random graphs and so on. So with that, just to summarize, basically what we're trying to build is a unified formal theory of the concepts important for beneficial AGI and draw implications for how AGI systems should and should not be designed, to say. In this talk, we talk a little bit about AGI safety problem solutions, incentives, agents, only briefly mention game theory and causality. As next steps, empirical investigations, like of this manipulation thing, practical algorithms, causal discovery on dependent mechanisms, generalized incentive analysis, multiple agents of dependent mechanisms, and just formalizing more concepts. And we do have this website where we list our papers and blog posts. So if you want to read more, that's what we do. Thank you very much.